Alright, chemistry, this is your video lecture for chapter 7, section 4. We're going to be talking about determining chemical formulas. Alright, one type of formula that we're going to determine or calculate, and it's going to be the first one you're going to need to do in the overall large problem, is the empirical formula. The empirical formula consists of the symbols of the elements combined in a compound with subscripts showing the smallest whole number mole ratio of the different atoms in the compound. Now this is going to be different than the chemical formula, which we will learn about later on. But first, let's start with determining the empirical formula. There are some steps, and here they are. First step, you're going to base all your calculations on a 100-gram sample of the compound. This is going to be okay for us to do for the same reason that using the 100-gram sample for percent composition was okay. Because no matter the size of the sample, the ratio, in this case, is going to be the same no matter what. So we can assume a 100-gram sample. And again, you could assume any size sample, any mass sample, and it would work out the same. We just choose 100 grams because it's a round number and it makes things a lot easier for us. So based on that 100-gram sample, we're going to convert how many grams of each element into the moles present of each element in that 100-gram sample. Then we're going to divide each value of moles, the number of moles for each of the elements, by the smallest of all the molar values. Then lastly, we'll multiply each molar value by that integer, by an integer, and we'll determine that at the time, to obtain all whole numbers. So we have to find whole numbers. And again, as we go through, have these 4 steps on your mind open to this slide so you can follow along. Alright, step 1, or part 1. So, adipic acid contains 49.32% carbon, 43.84% oxygen, and 6.85% hydrogen by mass. What is the empirical formula of adipic acid? Well, we're going to take, again, assume a 100-gram sample. And if we assume a 100-gram sample, that 49.32% carbon is actually going to be 49.32 grams of carbon, because 49.32% of 100 grams is 49.32 grams. All right, we'll take that value and we will convert it using dimensional analysis, like we've been doing, and we'll convert it to a number of moles of carbon. It'll look like this. All right, 49.32 grams of carbon converted into moles of carbon. We'll do the same thing for hydrogen and for oxygen, and we'll see that these 3 molar values here, we are going to bring these to the next step, to part 2. All right, so we're going to start with these values: 4.107, 6.73, and 2.74. We're going to start with those on the next page. This is where we're getting them from. All right, so this is step 1 of part 1. Moving on to part 2. We're going to divide each value of those moles, the ones that we just calculated, by the smallest of all the values. So again, carbon, we're going to take carbon, the 4.107 moles of carbon, we're going to divide that by 2.74 moles of oxygen. Again, because 2.74, if we go back, we see that the 2.74 moles of oxygen was the smallest value out of them all. So we will divide 4.107 by 2.74. We'll get 1.50. We'll move on for hydrogen. We'll take the 6.78 moles of hydrogen, divide it by 2.74 moles of oxygen. Again, because it's the smallest value. Then we get 2.47. Then for oxygen, do the exact same thing, and this one will obviously come out to be 1. These values right here that we've just calculated are the smallest, I guess I shouldn't say they're the smallest, but they are molar ratios. The ratio of carbon to hydrogen in this compound, for which we're trying to calculate the empirical formula, the ratio of carbon to hydrogen is 1.5 to 2.47. For oxygen to hydrogen, it's 1.0 to 2.47. So these are the actual ratios that these atoms occur, at which these atoms occur. But we can't leave it at that. We're going to move on to the next step. We're going to multiply each of those numbers that we just calculated. Again, the ones that we have red boxed out here. We're going to multiply those by an integer. I don't know which one yet. So that all of the numbers will end up being whole numbers. Now I need to multiply all of the numbers by the same value. So this will take some guess and check. But I'm going to skip to the chase. The carbon taking that 1.50, the hydrogen 2.50, and then oxygen 1.00. Again, you might notice that hydrogen isn't 2.47 like it was on the last screen. We're going to round that up. Okay? If it's within that small error, we can round this to a nice whole number. But only if it's 1 or 2 or 3 hundredths of a percentage or decimal off. Not if it's a third. Okay, not if it's 0.33 or 0.2 or 0.1. That's far too large. The difference of 0.03 is going to be completely due to an insufficient number of significant figures with which we're working. So we're going to use 2.5. Now, just by looking at this, you can eyeball this, and you can see, because there's some 0.5s, if I multiply everything by 2, I will get whole numbers. And so that's what I'll do. Multiply all of those values by 2, and I'll have whole numbers. So my empirical formula for this compound is going to be C3H5O2. And again, where did I get those subscripts? From these values which I just multiplied. Alright, so that was determining the empirical formula. Next, I am going to determine the molecular formula, which is, it's very different. It's the formula of the molecule as it occurs in nature, what it actually looks like. The empirical formula is the molecular formula with all of the subscripts reduced down to their smallest whole number ratios. So with the empirical formula, we just see what ratios these elements occur at. But molecular formula is going to be what how it actually occurs in nature. All right, so the empirical formula for adipic acid we just calculated is C3H5O2. The molecular mass of adipic acid is 146 grams per mole. What is the molecular formula for adipic acid? First step, we're going to find the formula mass for C3H5O2. Again, we've done this in the past. I'm just going to take into consideration the average atomic mass using my periodic table, and then take into account how many of each of those elements are present. Again, there are 3 carbons, 5 hydrogens, and 2 oxygens. So add those all together, carry out those different functions. We'll get 73.08. Taking into account appropriate significant figures. Yes. That'll be good. Alright. Part 2. Same problem. So we have the formula mass for the empirical formula. Then we'll divide the molecular mass, again, which is given in the problem, that 146 grams per mole. We'll divide the molecular mass by the mass given by the empirical formula. So that'll look like we have the 146 divided by 73 equals 2. You might ask, where did I get this 146 from? Well, I got it from the actual problem. Okay, the molecular mass is 146 grams. That's where I got this value. Where did I get this 73? I got it from the previous slide when I calculated the formula mass of the empirical formula for adipic acid. Step 3. Now, keep in mind that value that we just calculated was 2. The last step, we're going to multiply the empirical formula by the number we just calculated, and that will actually give us the molecular formula. So we'll take the empirical formula, multiply by 2. Again, that's what we calculated on the last slide. We'll have C6H10O4. Again, multiplying each of the coefficients, or not coefficients, I'm sorry, each of the subscripts by 2. Now, you will have some longer problems. Yeah, and this is what they will look like. Say, a sample has been analyzed. Here are the results. Compound is 18.8% sodium, 29.0% chlorine, and 52.2% oxygen. What is the chemical formula? And this is what we're going to do. Again, we've already talked about these steps, but this is the big, long process. Step 1, assume a 100-gram sample. Then your percent quantities become grams quantities, or they become masses. So we then have 18.8 grams of sodium, 29.0 grams of chlorine, and 52.2 grams of oxygen. Next, convert those masses into mole values. 18.8 grams of sodium ends up being 0.817 moles of sodium. 29.0 grams of chlorine end up being 0.817 moles of chlorine. And 52.2 grams of oxygen ends up being 3.26 moles of oxygen. Now remember, I need to find the smallest mole values here, and that's the 0.817. So I'm going to divide each of those values that I just calculated by the smallest value present, which is going to be that 0.817. Again, since your empirical formula is in small whole number ratios, divide your mole amounts by the smallest mole quantity, which is 0.817. After carrying out that calculation, we have the ratio 1 mole of sodium to 1 mole of chlorine to 4 moles of oxygen. And again, we don't want to get in trouble with rounding here. We don't want to round too largely here. This is 0.01 away from a whole round number, and that's okay. That we can chalk that up to significant digits, some imprecision there, but we're not getting anywhere close to 0.1 or anything like that. That's much too large. Moving on to step 4, we use these values and assign those values as subscripts in our formula. So we'll end up with Na1, Cl1, O4. But again, that's not how we write an appropriate chemical formula, right? NaClO4. But we don't want just the empirical formula. We need to move on and calculate the chemical formula. So we have to keep going. Step 5. In the event that the chemical formula is not the same as the empirical formula, and yes, sometimes they will be the same, sometimes they won't. You'll have to be able to figure that out. You need the molar mass of the desired compound, and you must compare it to the molar mass of the empirical formula. We'll do that here in a moment. Next step, divide the given molar mass by the empirical molar mass to get the multiple quantity. And then once you have that multiple quantity, you're going to multiply each subscript in the formula by that multiple quantity. So let's see what that looks like. So if I have the molar mass of the molecular formula, again, which will be given to you by a problem, okay, that must be stated in the problem, or something that you know off the top of your head, one way or the other. Let's just say for this example, it's 180 grams per mole. That is the molar mass of the molecular formula. Now, let's just say we went through and we saw that this compound had an empirical formula of CH2O. We find that the molar mass, again, just calculating using our periodic table, we find that the molar mass of this empirical formula, again, MMEF or sub-EF is the molar mass of the empirical formula, is 30 grams per mole. Well, I will divide the molar mass of the molecular formula by the molar mass of the empirical formula, and that should give me a whole number. In this case, it's 180 divided by 30. That comes out to be 6. And I'll take the empirical formula, again, 1 carbon, 2 hydrogens, 1 oxygen, multiply all of those subscripts by 6. And as a result, I'll get C6H12O6, my good buddy glucose right there. And this is the chemical formula for this compound. That'll be the end of the notes. At this time, I would like you to press pause and attempt these 3 practice problems. In one, I ask you to find the empirical formula, and in the other 2, I ask you to calculate the chemical formulas. Please press pause and attempt these problems now. Let's see how we did. We got CHCl3 for the empirical formula, and then for the chemical formula we have H2F2, and then we have C3H6. Again, if you're having trouble completing any of the assignments, please refer to the provided sample problems or bring your questions to class. I will see you next period.